Many solid chemicals will absorb water out of the air. We call such chemicals hygroscopic. Now, what happens when you try to weigh a hygroscopic material? As water is absorbed from the air, the mass of the solid continues to climb. And this makes it very difficult to obtain an accurate mass when weighing hygroscopic materials. And so we need another method to accurately determine how much we have. We often use a process called standardization to accurately determine how much we have. Sodium hydroxide is hygroscopic, and in this experiment, you'll use an acid-base titration to standardize a solution of sodium hydroxide. Note that you'll probably actually be using potassium hydroxide in place of sodium hydroxide. Now the chemistry is identical, so I'm going to use sodium hydroxide in my explanations, but you can mentally replace sodium hydroxide with potassium hydroxide. A titration involves reacting a solution of unknown concentration with a known quantity of another chemical. So we have something like this. The titrant is the solution that we have in the burette, and the analyte is the solution in the flask underneath. In other words, we're slowly adding the titrant to the analyte until we have added exactly equal quantities of titrant and analyte. Based on that, we can then determine the concentration of the unknown solution. In our experiment, we're going to use potassium hydrogen phthalate, which we'll abbreviate as KHP, as the acid, and we're going to put that into the flask. Now, KHP is not hygroscopic, and so we can easily measure the mass of KHP that we put into the water here to determine how much KHP we have, how many moles of KHP we have. Then, we'll add a base, we'll add the sodium hydroxide slowly until we have added exactly equal quantities of the sodium hydroxide and the KHP. Now, the KHP is an acid and the sodium hydroxide is a base, and that means that we have an acid-base reaction occurring. We have KHP and we're adding sodium hydroxide to it. We're removing the hydrogen here, so we'll have potassium sodium phthalate and water. And so we are neutralizing the KHP. So we're going to start with an acid in our flask. We can then monitor the pH using a pH sensor, and we'll observe the change in pH over the course of the reaction. So as we add volume of titrant, as we add sodium hydroxide, we will observe the pH. So again, we're starting out with an acid in there. So if we plot pH versus volume of sodium hydroxide added, we should start out with a low value, and we'll slowly see the pH rise until we get very close to the equivalence point. The equivalence point is the point at which we've added exactly equal quantities of titrant and analyte. And then the pH will change really fast, and then it will start to level off again. So we'll have a curve that looks something like this. It'll be this characteristic S shape. So how do we know when we've reached the equivalence point? Well, one way we can do it is by adding an indicator, and if that indicator will change color as the pH changes, then we can use the color change to identify when we've hit the end point. And we are, in fact, going to use phenolphthalein. Phenolphthalein changes color from colorless at pHs below 8 to a vibrant pink color at pHs above 10. And so we can use that to identify an end point. But note that the end point and the equivalence point are not necessarily the same point. Ideally, yes, they would be the same point, but often in practice, they're slightly different values. The equivalence point is when we have added exactly equal quantities of the titrant and the analyte, but the end point is often when we first know that there is some change, like when the indicator begins to change colors. But remember I said that phenolphthalein doesn't change color until between 8 and 10. So at that point, we are probably already past the equivalence point. So let's go back to our pH curve. So we initially said that the pH started out low because we have an acid in there. And as we start to add base, the pH is going to start to climb because we're reacting away the acid. So we have less acid, it's going to get closer to a pH that is neutral, a pH of 7.0. Once we've reached the equivalence point, we have reacted away all of the KHP with our sodium hydroxide. We have none of either of these left. All we have left is water. That's going to have a pH of 7. And we have sodium potassium phthalate. So the question is this going to change the pH, or are we going to have a pH that is exactly 7.0? Well, we know that our sodium hydroxide is a strong base. That means that its conjugate acid is a negligible acid. But KHP is not one of our strong acids. That means that it's a weak acid, and a weak acid has a conjugate base that is also weak. That means that this base, this phthalate ion, is also going to be a weak base. So we have a weak base and we have water. That's going to be neutral. That means that we're going to have a basic solution at the equivalence point. So we would expect the pH at the equivalence point in this titration to be above 7. But where above 7? That's going to depend on the concentration that we have. And that is going to depend on how much of our sodium hydroxide that we've added. Because we know, we can identify how much KHP we've added, but then we're going to add some distilled water to the KHP to dissolve it, and then we're going to be adding some sodium hydroxide. And the sodium hydroxide that we add is going to be diluting, it's going to be adding volume to the flask, and that means that we're going to be slowly diluting the KHP that's there, even ignoring the fact that we're reacting some of it away. So some point in here is the equivalence point. I'm going to call it this point here, equivalence point. So if we look at our titration curve, we have our equivalence point, and past that, if we continue adding more sodium hydroxide, well, at that point, at the equivalence point, we've added exactly equal quantities of KHP and sodium hydroxide. We have none of either left of them left, but we have some sodium potassium phthalate. As we add additional sodium hydroxide, we now have our weak base, the phthalate ion, and we're now adding more sodium hydroxide. There's nothing left for the sodium hydroxide to react with, because a strong base is not going to react with a weak base. We have no other acids because we've reacted away all of the KHP. And so now we're just adding more strong acid, and it's just building up into the flask. It's going to be more dilute than it is up here in the titrant because we have more water around, but that's why the pH continues to climb. And it eventually levels out because the concentration in the flask here can never get any higher than the concentration is up there in the titrant. Okay, but how exactly do we identify exactly where that equivalence point is? This can be fairly challenging for us to do. If we look initially, the pH curve is curving upwards here, and after the equivalence point, it's curving downwards. So the equivalence point is the inflection point. It's the point where the pH curve changes from curving upwards to curving downwards. In other words, it's the maximum slope in there. Now, on that graph, it's fairly challenging for us to eyeball where exactly that maximum slope is. So let's see if we can perform some calculations to nail down exactly where that is. Let's take the first derivative of our pH curve. The first derivative is going to be the slope of this curve. So the slope is initially going to start out pretty low. It's going to get much higher as we approach that equivalence point, and then it's going to drop back down to 0. So the first derivative is going to look something like this, where we start out as initially low, it's going to have a higher value. I've made this much wider than it really would be for this graph. But the equivalence point is then the peak there on the first derivative plot. And so, okay, we can relatively easily identify what is the maximum value in there, but we may have some noise in there. And so if we have some noise, then it may not just be as simple as saying the maximum point. So let's take the second derivative of the pH versus volume curve, which is just the first derivative of the first derivative curve. So we're looking now at the slope of this curve. So the second derivative is going to be the slope of that one. It's initially going to start out at 0. It's going to get higher as we come up here, and then it's getting back to 0, and then it's becoming negative. So I'm going to draw this 0 line there. It's starting out 0, it goes up to some positive value, and then it crosses the axis, comes back up, and it's going to stay negative, ignoring any noise. It's going to stay negative forever. But get much closer, asymptotically approach 0. So the equivalence point is then this point where we cross through the 0. And this means that it's relatively easy for us to take a section of data in here and plot a linear trend line in there and solve that trend line for y equals 0. What is the x value? What is the volume of sodium hydroxide added? That gives us a value here on this second derivative curve equal to 0. And that is going to be our most precise measurement of the equivalence point. In this experiment, you are going to create a solution of sodium hydroxide that you are then going to standardize to identify the concentration of, and then you're going to use that solution and its concentration in the next few labs. So make sure that you label that solution. You'll have a storage bottle to store it in. Make sure you put a label on it with the concentration and your name or initials, and store it in your lab drawer or cabinet for the next few labs. You're also going to take that solution and put it into a reagent reservoir that functions similar to the burette. That reagent reservoir is going to look something like this. There are going to be 2 valves on them. You're going to use the bottom valve as on-off. It's either fully open, where the flow is going to go through, or it's fully closed, where the flow is shut off. The top valve you're going to use to control the rate. So you're going to very carefully adjust the angle of that top valve so that you set a flow rate of about 1 drop per second. You don't want it too fast, or the pH probe won't be able to keep up, and the drop counter also is much more likely to lose count of the drops. You don't want it too slow, or the reaction will take an extremely long time. So the top valve, once you set it, for the speed, you do not want to touch that top valve again. You're only going to use that bottom valve for open and close, and leave that top valve alone for the entire rest of the lab. Now, you're also going to have a drop counter, and we have 2 different styles of drop counter. We have this style, which is the slightly older style, and the drops get counted as they fall through this slit. And then we have the newer style, which is this one, where the drops get counted as they fall through this opening here. Now on this one, it's fairly easy to tell if the drop counter is counting correctly because there is this red LED that flashes every time the drop counter counts a drop going through. On the older style, we don't unfortunately have that LED present. And so it can be a little bit more challenging. You have to really carefully watch the data on your LabQuest to identify whether it's counting drops. Now, with the newer style, you want to position the tip of your reagent reservoir where it's dripping your sodium hydroxide through this gap. Now, you don't want it in the space, because if the tip or the drop that's still on the tip is in that space, then it's going to be counting the tip and not, or the drop on the tip still, and not a drop that has fallen through. So you don't need to have the tip really close to the drop counter. You don't want it super far apart, but you want it maybe an inch above or so that the drop is falling through the space in there. With the older style drop counter, it's a little bit more challenging because you have to get the drop to fall through this gap. It needs to be centered in that gap. So you want to adjust the tip of your reagent reservoir, not too far one direction or the other. You want it just above. Again, you don't want it inside that gap. You want it above, about an inch above, but make sure that it's centered. So as you're looking down this direction, down the drop counter, you want to make sure that the tip is centered in that gap so that the drops will get counted. Let's also talk a little bit about the pH probe that you'll use. The pH probe will come stored in a bottle that looks something like this. That bottle should have some liquid in it, because at the bottom of the pH probe, we can release the pH probe by loosening this nut at the top of the storage bottle, releasing the pH probe. At the bottom of that pH probe is a little glass bulb. Now, that glass bulb has a very thin wall to it, and there are some plastic pieces around the pH probe to try to protect that glass bulb from contacting anything else, but you also need to be super careful not to have anything smash into that glass bulb, because again, it is very thin glass and it fairly easily will break, and that ruins the entire pH probe. Now, if you noticed, when I took the pH probe out of the solution that it was stored in, I took the Kim wipe and I wiped off that glass bulb at the bottom. You want to do that, but you also want to take some distilled water or deionized water in a squirt bottle and squirt the entire bottom of the probe, including that glass bulb, rinse it off really well into a waste beaker, and then take a new Kim wipe and blot the sensor dry. Now, by blotting it dry, we don't want the sensor to actually dry out. That's why it's stored in a solution. Because if that glass dries out, then the pH sensor takes an extremely long time to respond to pH changes on the outside of the glass. So you should always have the pH sensor either in the solution that you're measuring the pH of, or in that storage solution. If it's out for 30 seconds or so, that'd be fine, but don't leave it exposed for more than just a minute or two. If it's going to be longer than that, then put the pH probe back into the storage solution so that it stays wet. Also, make sure that you store that storage solution upright so that the pH probe is down in the liquid inside the storage bottle. So let's talk about safety. Sodium hydroxide is extremely corrosive to human tissue. Clean up any spills immediately, and if any touches your skin, wash the affected area immediately.